Okay, so I want you to consider a thought experiment, which is, let's say we were to do a coloring process on this square, and let's say it's just like a 1 unit by 1 unit square. Let's say the coloring process I was going to do was I was going to divide it in half, and then I want to color that first half, okay? All right, and then after that, let's say color a little better than I color. I want to color half of what remains. Okay, so let's keep track of what I've been coloring so far. So I colored half of the original square, and then I'm going to color half of what's remaining. Okay, so I can actually write it in here. So I colored half, and then this is really 1/4 of the original square, right? And I can color that in, okay? And then let's say I want to again color half of what's remaining, okay? So if you think about it, that's going to be 1/8 of the original square, and I can color that in. Okay, and then like from this point maybe I want to continue to color half of what's remaining. So this is going to be 1/16, okay, of the original square. Okay, that gets colored in. Now it's getting harder to do at this point, but if you think about it, okay, what's half of that? Then the next thing that I'd be coloring is 1/32 of the original square, okay? And then next thing, it's really getting so that you really can't represent it very well anymore, but the next thing would be 1/64 of the original square. Okay, so you get the idea of what's going on. Getting off the page here. Okay, so in other words, what you're actually doing is you're coming up with a geometric series, and hopefully you can see like in this one, the first term is 1/2, and then I multiply by a half times a half times a half times a half, etc. If I were to consider doing this coloring process, I kind of could consider doing it forever. Obviously, I'd run into limitations with the pen thickness and the detail that I could accurately do with my fingers and so forth. So there's actually practical limitations. But I could color like this forever, where I just color in half of what I colored before of the remaining parts of the square. So hopefully you see through this process, like if I were to color forever, I would color the entire square. So let's kind of see how that would work out. Okay, so it turns out that this is an infinite geometric series, and so what I'm going to go ahead and tell you is that the sum of an infinite geometric series is the first term over 1 minus the ratio. Okay, so I actually put it in words here, but sometimes you'll see it as like A1 over 1 minus r. Okay, so if we were to run this through with these values, let's see what would happen. Okay, so the first term is 1/2, right? And then the ratio is also 1/2. So the numbers are pretty easy in this case. Okay, so I get 1/2 over 1 minus 1/2, okay, which is of course 1/2 over 1/2, which is 1. So in theory, if I were to continue this coloring process forever, I would color the whole 1 by 1 square. Or, I mean, alternatively, you can see if I'm just adding up this sequence of numbers, this series of numbers, that series of numbers should total up to 1. So you might ask, why did this work for an infinite geometric series, and when does it work for a geometric series? Okay, so let's start out with what we had last week. This is the sum of the first n terms of a geometric series. Okay, so now what we would like to study is what happens when the ratio is less than 1. Okay, so when the ratio is less than 1, like let's just look at something like that. So 3/4, okay, and then we have like say 3/4 squared, which is 9/16. That's getting smaller, okay? And so let's say we had something like ... like 3/4, say to the 50th power. That's going to be very, very small, okay? So what's happening is you're adding things which are getting smaller and smaller and smaller, and eventually they're becoming almost negligible in terms of what you're adding, okay? And so in other words, they come closer and closer to 0 what you're adding when you get really far down into a geometric sequence like this, okay? So what that means is this r to the n, if r is less than 1 in absolute value, is heading to 0. So what that's going to give you is that the sum, of course it's not s sub n anymore, we'll really just call it s because you're summing the whole series, is just going to be a1 over 1 minus r. This goes away, so it's just a1 times 1, so just a1 over 1 minus r. Okay, let's do some more examples of this. Okay, so let's look at a couple different examples. Let's say we want to look at 3/4, okay, and then plus 9/16, okay, and then the next one will be 27/64, etc. How would we find the sum of that, the infinite geometric series? Okay, so it's just going to be the first term, okay, over 1 minus the ratio, and in this case the ratio is the same as the first term, but they can be different, and they often are different, but in this case they're the same. Okay, so it's just going to be 3/4, and then 1 minus that is going to be 1/4. So then of course this is just going to simplify to 3. Okay, let's look at another example. Let's change that above example to be alternating. So if it were alternating, it'd be 3/4, then minus 9/16, right? Then it'd be plus 27/64, okay? And of course the next term would be a minus term. Okay, so in this case the multiplier from term to term is going to be negative 3/4. That's going to be the ratio that you get if you put a term over the previous term, or that's going to be the multiplier you're going to use. Okay, so in this case we would do 3/4 and then 1 minus the ratio. You have to be really careful because you get two negatives in here. 1 minus that negative number. Okay, so it's going to be 3/4, and then here you're going to have 1 plus 3/4, right? So 3/4 over 7/4, right? So then that's going to, of course, simplify to a number of, or a sum of 3/7. So because there's some canceling out back and forth, you see that, like, you know, some of the positive stuff gets canceled by some of the negative stuff. So it kind of makes sense that the sum would come out to something like that for this one. Okay, of course you have to be very careful that you can only apply this formula when the sum actually, or when the ratio is actually less than 1 in absolute value. Okay, so let's look at another one for a minute. Okay, let's say we have 4/3 plus, then we have 16/9, then the next one is going to be 64 over 27. So what's happening here? I'm multiplying by 4/3 from term to term to term. Okay, because that ratio is bigger than 1, this series is going to do what's called either diverge, or you could say it does not converge. Okay, so that means that basically it's going to add up to something infinite. Okay, or it could be infinitely negative if it, you know, we're all negative, that sort of thing. So that's what happens with most infinite series, obviously, except for the special case of when the ratio is less than 1 in a geometric series or another couple series that you might study in the future. So let's look at, for instance, an arithmetic infinite series. If you think about this one is going to always continue to grow, okay? You're always adding more to it, and so you're never adding an amount that's just so small that it's going to be negligible to the total, like it is in a geometric one where it just gets so infinitesimally small that it hardly matters anymore. An arithmetic infinite series, if it's truly infinite like this and you're just adding arithmetic terms, it's going to diverge. Okay, I would like to solve a debate that's been going on for many, many years, probably in people's heads, which is, what is this? Okay, So let's think about if we can rewrite this as a geometric series. Okay, so I could go ahead and, so 9 bar would be repeating 9, so it's going to be 0.9 plus 0.09 plus 0.009. And if I really added all of these up, I would get 9s repeating forever. But I just kind of wrote them out with separate place values, basically. Okay, so this is going to be an infinite geometric series written out like this with a multiplier of 1/10. Okay, so I just do the first term, okay, over 1 minus the ratio. So the first term is 0.9. It's going to be 1 minus 0.1 or 1/10. Okay, so I get 0.9 over 0.9, which is in fact 1. So, you know, there have been many students I've had over the years that said, well, this is not equal to 1, but now you know that this value actually is 1. Okay, let's look at something that looks more abstract, but is actually not that hard. Let's say we have something that looks like x plus x over 4, okay, plus x over 16 plus ... Okay, so the question is, can we find some representation of that infinite sum? Okay, so it turns out, if you think about it, that all I'm doing to get from term to term is I'm multiplying by 1/4 each time, okay? And then of course I have the first term is just x. So using the formula, the first term over 1 minus the ratio, it would look like this. Okay, so that's just going to be x over 3/4, right? Which would be the same as multiplying by the reciprocal in the numerator. So 4x over 3 would be the sum for that. Okay, let's do one more type of problem. Let's say we have a field, and we're going to say our field is 100 meters long, and there's a bug, and the bug's going to do the following. The bug is going to go 3/4 the way down the field, okay, it looks a little bit more than that, and then he's going to fly 3/4 of the way back that he just did, and then he's going to go 3/4 what he just did that way, he's going to do it that way, and then he's going to go back 3/4 of what he just did the other way. Okay, so each time he does 3/4 of the distance that he did before, but he does it in the other direction, and he does that forever. Okay, so let's see how that kind of looks as a series. Okay, so the first thing, he does 3/4 of that distance, so that's going to be 75 meters, and then he's going to do 3/4 of that, and then he's going to do 3/4 of 3/4 of that. Okay, so each time he just does 3/4 of what he did the previous time. Okay, and that goes forever. Okay, so the question is, how far would the bug travel in total over this whole scenario? Okay, so again, I'm going to do the first term, okay, over 1 minus the ratio. So it's just going to be, the ratio is going to be 3/4, so it's just going to be 1 minus 3/4. Okay, so it's going to be 75 divided by 1/4, which is 75 times 4, which is 300 meters. Okay. All right, so let's ask another question, which is, after a sufficiently long amount of time, where about is the bug going to be? Okay, so obviously, you know, we can't be forever with him, but and he won't be there forever, obviously. But I want to say, if you go sufficiently far down this series, you're going to kind of pinpoint about where he's going to end up. Okay. All right, so let's think how that's going to work. Okay, so let's go back to the beginning drawing again. Okay, so the first thing that happens is he goes 75 meters this way. Okay, then he actually goes backwards. So what we can do is represent this way as a positive value, and going backwards as a negative value. So there's a positive value, then a negative value, then a positive value, then a negative value, each time being 3/4 of like what it was before. Okay, so if we build that up, it's going to be 75, okay? And then he's going to travel in the other direction for that length, okay? And then going back to the positive direction for the next length, and so forth, okay? So in this case, what's going to happen is we're going to have the first term divided by 1 minus the ratio. And in this case, it's going to be 1 minus negative 3/4. Okay, so it's going to be 75 over, if I combine those together, it's going to be 1 plus 3/4, right? So it's going to be 75 over 7/4, okay, which is going to be the same as 75 times 4/7. So I can actually figure out what that is on the calculator, and I get approximately 42.86 if I round it, say, to the nearest tenths place. So after a sufficiently long period of time, doesn't have to be infinitely in the future, but you know, the increments that you're going to be adding in the positive and negative direction after sufficiently long are going to be just so negligible that that's going to be sufficient to approximate where he is after a while. Okay, so you might think at the beginning of this problem maybe he'd end up in the middle of the field, but it's actually kind of biased. It's more toward the first direction of the travel, if you think about it, because again, it's like the distances are measured positive from this way. So he actually ends up this many meters, say wherever from the start position that he originally started from. So to recap, the things you need to know are, if you have an infinite geometric series with the ratio less than 1, this is going to be how you're going to find the sum of that series. Okay, so again, it's very important that the ratio is less than 1, because if the ratio in absolute value is not less than 1, then it's not going to converge. You're going to get an answer that doesn't make any sense. It's usually like a negative value or something like that if you try to apply the formula where it doesn't work. So again, this thing only converges when the ratio is less than 1. Otherwise, you say it's going to either not converge or diverge.